So let's finish this quotient property by looking at number 10 in your textbook. So 10a, now we're going to write these expressions as a single logarithm. And there's a good chance we're going to have to use both the quotient and the product property to do that. All right, so we can do these using the order of operations. So we can apply quotes PEMDAS from left to right. In fact, that's what we have to do. And as we move left to right, we're going to take this and rewrite it as a quotient. So when I see subtraction, that means we can rewrite this as common log of x divided by 4. By the way, you need to be very careful to note that the bases of the logarithms must be the same to apply the quotient and product properties. Okay, and now we have addition. And so we're going to take a single logarithm of x divided by 4 times z. When you do that, you need to think about this as z over 1. So top times top, bottom times bottom. This becomes x times z divided by 4. Final answer. Okay, and then for b, this is 10b, we've got, again, common log of x minus, now we've got parentheses, log 4 plus log z. Now, because of the parentheses, we're going to do what's in the parentheses first, meaning this is a product, so I'll rewrite this as log 4z, and then that's going to be subtracted from the log of x. Now, this second set of parentheses, or this parentheses here, wasn't really necessary. I just left them in to help us keep track of where things went. Now we're going to apply the quotient property because of the subtraction. And that means we're going to do log x divided by 4z. Notice the difference between these two. Here, the z ended up in the numerator of our single logarithmic expression, and here the z was in the denominator because of the parentheses there. Easy place to make a mistake. Just be very careful as you put these things together. All right, now we're going to do what it says here in the textbook. We're going to go ahead and switch over to a graph for number 11 and sketch these two things. So let me get a quick new graph here. And in number 11, we're to graph log x, y equals log x plus log 4. And then we're to graph y equals log of x plus 4. Notice these are very different graphs. So we're highlighting here that when we are doing addition within the logarithm, within the argument of the logarithm, that is not the same thing as what we've just been doing as the quotient and product properties. In other words, it's a really easy mistake to make, and we're trying to highlight this so that you won't make it. So take a look at letter C. Here, let me cover up that answer. It says, what do the graphs suggest about the relationship between log base a plus b and log a plus b? Hopefully, it's very clear, because those graphs are so different, that this is not equal to each other. Now, a mathematician would be like, come on, of course that's not true, right? We showed that log of a times b is equal to log a plus log b, right? In fact, we did the more general case where we put in a b here. So it didn't matter the base, that those two sums, that product is equal to the sum. So there's no way this is true. Now, we might be able to find a special case where a times b is the same thing as a plus b, but let's not muddy the waters and get ourselves confused. Let's just note, don't make this mistake. Don't try to split the sum that's within a logarithm into two separate, or the sum of individual logs. So our final property is called the power of a logarithm. And we're going to switch to decimals real quick and check it out. As you can see there in your textbook under 12a, it says we want to graph these two functions. So I'm going to do f of x equals log base 3 or log of x cubed. So log of x cubed within the logarithm, and then I'm going to do g of x equals log 3 times log x. Now, don't look at the graph because it gives away the answer right away. So let's go ahead and fill in this table, and I want f of x1 and then I want g of x1. And our textbook asks us to evaluate what's up with 2. What's the result? 7 and 15. And when you look at those, oh, right, they're exactly the same. So these two expressions are equivalent. So what we've done is we've made an argument that says, hey, when we have log base 10 of x cubed, that's equal to 3 times log of x. We showed that graphically, that this is true. They're the same thing. We also did a numerical argument that when we evaluate those points, they're the same. This is not at all a proof. So don't think that we've proved that they are the same, but we're just going to tell you in general, this is true regardless of the base or the exponent. In other words, down here is the property of logarithms. We're using a's and p's. So if I have log base b of a to the pth power within a logarithm, within the argument of the logarithm, that can be written as p times log base b of a. In other words, we can bring that exponent within the logarithm, bring it outside and multiply by it. That should make sense because a logarithm is an exponent. Whatever this log base b of a is, remember it's b to some power equals a. So the answer to this is that question mark. And so if we have the thing in here being raised to a power, multiplying those exponents together should be the same, because when we did a times n to the m, we knew that that was just the product of the two powers. So this is essentially the same idea. So let's check out a few practice problems here on page 365, number 13a, we'll start with. And the directions are to use the properties of logarithms to write the given logarithm as the sum or difference of two or more logarithms, or as the product of a real number and a logarithm. And then we're told that all variables represent positive numbers. Important point, if they weren't positive, we wouldn't be able to evaluate logarithm of them. Okay, so here we have x to the 1/2. Log base 3 of x to the 1/2. Well, that's an exponent, right? So we, by that property we just noted, we could rewrite that as 1/2 times log base 3 of x. Quick note, never mind, we're going to get it in a second. Okay, so letter B then is log base 5 of x cubed. To a mathematician, this is the exact same problem as that one, even though the numbers are different. This is an exponent within the logarithm, so we'll do 3 times log base 5 of x. Done. All right, letter C, ooh, it's like the same thing again, right? In this case, it's log base e, or natural log, of some base raised to a second power. So because this is an exponent within the logarithm argument, we just multiply by it. 2 times natural log of t. Here's the one that I was going to mention back in A. What's up with log 10, common log, of the third root of 50? Well, recall that the nth root of some expression can be written in rational exponent notation, 1/n. In fact, remember we put an m here just in case we're raising that to a value, and then an m there, same thing. So this is really log 50 raised to the 1/3 power, which then means we can bring that 1/3 out and just do 1/3 times log 50. Now wait a minute, isn't 50 10 times 5? Of course it is, right? So that means we can rewrite this as 1/3 log of 5 times 10, which we can then split into two separate logarithms in the sum of those, but we'll need parentheses because this 1/3 is times this entire logarithm. So when we split it, we need to apply it to both. But wait a minute, doesn't this base match that base? Well, yeah, it does. They're both 10. So that means our result here is 1/3 log 5 plus 1/3 times 1. Notice I did two things at once here. Maybe I shouldn't have. I distributed the 1/3 to both of these, and I noted that log of 10 is 1. So this answer, it could be this. You could leave it in this factored form. Depends on the context of what you want. Either way, either of those answers correct. You'll have to note carefully what MyMathLab wants. All right, let's do a little more complicated one. This would be letter E. So here we're to take log base 5, and remember our goal is to rewrite it as a product, sum, and multiplication by real numbers of logarithms. So because of this division, we'll take care of that first. We can rewrite this as log base 5 of x squared y cubed minus log base 5 of z. All right, and then we have to be careful here. I can't put a 2 outside and a 3 outside of this because this isn't a base raised to a power. It's two different bases, each raised to different powers. So we can apply the product rule because this is x squared times y cubed. We could rewrite this as log base 5 x squared plus log base 5 of y cubed. Don't forget this mess we already wrote down. Nothing else we can do with that subtraction part. Well, now we can bring these exponents out front. We can multiply by them. So final answer, 2 times log 5 of x plus 3 times log 5y minus log 5 of z. A little bit complicated, right? But we're just applying those three little properties. Good news is logarithms really are governed just by those three properties, where the exponential things were governed by like 8 different properties, if you recall. All right, let's go ahead and do F. So F says take log base 3 of 3x squared divided by y cubed. As before, I'm going to go ahead and do the quotient property first. So that's log base 3 of 3 times x squared minus log base 3 of y cubed. And then I'm going to do the product property just like I did up here. Note, again, as I mentioned before, you need to think of 3 and x to the third as two numbers. There's not really, 3 is not connected to x cubed in any way other than it's a product. And because it's a product, we can rewrite it as log base 3 of 3 plus log base 3 of x cubed minus log base 3 of y cubed. This is 1. Bases match, and then we'll multiply by 3. So this really becomes 1 plus 3 log 3 of x minus log, and then this would be 3 log 3 of y because that's an exponent there. Now, if you're someone that's noting what's going on here and you're like, hey, I could do this I could go from here to here. Great, do it. I don't have a problem with that. If you're getting really comfortable with these logarithms and you can see the stuff, you don't have to show tons of work to get it done, especially in MyMathLab, right? MyMathLab just cares about the answer. Okay. For the next video, I'll put the change of base formula and going backwards, going from this form to that form, which is arguably more difficult in the next video.